Welcome everyone to this Martin Audio webinar. Today we will be, if I can find my mouse, we will be looking at MLA. So that is our large format multi-cellular loudspeaker array system. We're going to be kind of looking at the different ways the system is used and the different kind of parts that make up this loudspeaker series or this loudspeaker range. So my name is Simon Purse. I'm a product support engineer at Martin Audio. It's my job to present training, to create training, obviously online and in the workshop, in the office when we're going back to normal. I'm joined online today by my colleagues Robin and Joe. So Joe's obviously over in the States, Robin's in the UK here with me. So if you have any questions, just type one out in the question box and I'm sure one of them will jump on it and we'll have a Q&A at the end if not. So let's just crack on with a bit of an overview of the wonders of MLA. So we actually have 3 products in the MLA series. So we have MLA, MLA Compact and MLA Mini. MLA Mini is a double 6.5 inch, so quite a small install box. People also use it for kind of theatre works, small gigs, corporate stuff. And we have Compact, a double 10 inch, slightly bigger. This is used on, theatres, festivals, anything where maybe even a load weight restriction is going to cause you to not use a full format system. And of course we have MLA, which is our double 12. And this is quite a revolutionary speaker system when it came out. Although it's about 7-8 years old now, it's still very much at the forefront of sort of line array technology, or I shouldn't say line array, loudspeaker array technology. This system allows us to control an SPL profile from the front to the back of an audience, so we can actually, within reason, dictate how the SPL drops off from the front row to the back row and kind of control how that gradient happens from across that region. We can also control areas that we want to actively avoid. So if there is a balcony causing reflections, we can use this technology to try and remove some of the effects of that reverberant field on the rest of the audience. So this is very much about increasing the direct signal to the audience areas and avoiding the areas that you do not want to have any reflections or reverberations from. We also use this same technology, as well as creating an even SPL profile from front to back. We can also create an even tonal response from front to back. So we're actually trying to make the audience area as even as possible. So everyone's paid the same price for a ticket. Everybody should have the same sort of immersive feeling and the immersive experience of audio anywhere you are stood in the crowd. So what makes this system different to conventional line arrays? In the beginning, which is still very commonly used to this day, is just a one-zone line array. We've got control over the LF, the mids, and the highs. And here you can see you've got one channel of DSP for each of those different areas. Moving on to band zone arrays, which is much more common now, and indeed with our older series, so like W8LC, for example, we have a band zone array. We have an array which has been broken up into one signal chain, in this example, one DSP set for the LF, 2 DSP sets for the mids, and 3 for the highs. So here we've actually broken up the line array into different areas, which gives us different DSP control over different parts of the audience. As the bottom of the array is obviously covering the front, the mid is covering the middle, and the top of the array is obviously throwing to the back of the room. So we want different DSP control for each of those. But since we've gone to the extent of breaking up these areas, we've actually stopped the kind of uniform coupling which you would generally see from a line array. And if you're going to break it up to a small extent, you may as well break up the system in its entirety and have this multi-cellular approach, which we now see with MLA. So this is no longer a conventional line array or a line source, so to speak, as we've kind of lost the coupling that you would expect from each one of these different cells in their own right, so HF, the mids and the lows. And now we have independent control of every single cell in each cabinet. So there's 6 channels of DSP in each MLA cabinet. So with a 24 box array, we actually have up to 144 channels of DSP and amplification in every single array. So in the box itself, obviously we have 2 LF sections, which we're going to look at in a little bit more detail. Obviously we have 3 HF and 2 mids. So we're actually using 1 channel set of DSP for the LF, simply because of wavelength. It would not make particular sense to have 2 independent channels. But then we have individual control of the mids and individual control of the HF sections. Each one of these has a parameter set, which is calculated by our display software. And that allows us to do some very clever things in terms of, I don't like to use the word beam forming because that seems a bit of a hot topic these days, but we can control the dispersion, the vertical dispersion of the array through these filter sets beyond just the mechanics of the actual splay angles themselves. So with directivity and control, we have an array and our audience area. And of course, with this technology, we are able to create an even tonal and SPL response from the front right the way through to the back of the audience. And additionally, we can actually choose to actively avoid an area. So in this example, we are avoiding the stage. But of course, as this is a powered and networked audio device, we can actually change this on the fly. So if the neighbors towards the back of the field start to complain, we can then change our DSP goals and our parameters, and we can now actively avoid the audience, not the audience, sorry, the listeners at the back of the field where they're not necessarily part of the gig and don't want to be part of the gig. And we do this through our display software. So this is just a cutout of the coverage window. It's a very almost crude looking image, but don't let the software front fool you on the complexity of what this software is capable of doing. So here you can see we have blue sections, we have red sections, and we have green sections as we kind of move around the periphery of this venue. So this is an on-axis slice that we call it, which is a kind of on-axis cut through of the venue, on-axis to the, sort of straight onto the array. And as we can see, we're looking at the vertical dispersion or the vertical splay angles in the relationship of the line. We're actively avoiding in this situation the stage. As you can see, I've selected this to be a hard avoid location, and also the first front of the balcony we're also avoiding, because in this particular example, say this the front of the balcony there is made of glass, it's particularly reflective. It's not causing a particularly pleasant experience or a coherent experience for the members of the audience, which are quite close to it, as they're hearing this sort of this echo or a flutter coming away from it. So we're actively avoiding this area. And with this technology, we can select the areas that we wish to avoid, the areas that we wish to cover, as you can see shown in green, and areas shown in red, areas we're not particularly bothered by. You'll also note on this diagram here, there is a 0 dB point. This is our reference level. So this is could be set anywhere that you wish. At the front of the audience here, it says 1 dB, and at the back there, right at the top, is -2. So this is actually set automatically, which isn't public release yet, but coming up in the next few weeks, we'll have a new version of display where we can automatically set the SPL profile according to the line length and proximity of the audience area to the array, and a bunch of other factors which we take into account. But here we can see the array is going to make the SPL drop by 3 dB from front to the back. We're going to have a deeper look at that later, but this is just to show you that this is quite a powerful piece of technology and the level of control that it gives you. And due to that control, we have used this system on a lot of large-scale gigs where leakage into the area beyond the festival itself or the gig itself is a real issue, where you have neighbors which are going to complain, and if they complain enough, this gig's not going to happen. So here we have Glastonbury Pyramid Stage. This is a huge gig in the United Kingdom. I think when the field is full, it's probably about 150,000 capacity. and this system really is quite large, but with this MLA system, we're able to achieve higher SPLs at front of house than ever before, whilst keeping the spillage into the local area as reduced as possible, so we can have it louder in the crowd and quieter off-site. And that is only possible because of the MLA technology that we are using. Same again in the Hyde Park in London. So the neighbours in this part of the world probably own some of the most expensive real estate that you can buy. When they complain, generally the council starts to listen. So we need to have this very strict SPL profile from front to back, and then drop away as soon as we start leaving the park, to make sure that the neighbours and the residential community beyond do not get affected by the gigs that we're putting on there. And again, in this situation, we are able to have sort of record levels of SPL at front of house and throughout the audience, whilst maintaining this reduced level off-site, which again is only possible because of our MLA technology. And because of this, we have, of course, won a lot of awards, be this for install, touring, or any other use of our systems. So let's have a look at our MLA loudspeakers themselves. Excuse me. So this is a large format, three-way or horn-loaded line source. We have a 4-point rigging system where we can have up to 24 boxes in an array. Obviously, using our display software, if you're not familiar with it, there is a bunch of other webinars online. There's loads of videos on YouTube if you want to learn a little bit more about that. But display angles between the boxes are calculated within the software, and this will tell you if you need to pass BGC V1 or any of the DIN certifications that you might need for other parts of the world. But you can fly up to 24 boxes, but it will not pass BGVC1. We have 1 or 2 point flying, and you can also ground stack these boxes. So if you have the benefit of 2 motors, which I would definitely suggest with a box of this size, then of course that's advisable. If you only have 1 motor, then display will tell you which hole you need for the angle that you require. And of course, you can ground stack on these on these flying claims as well. We're constant 90-degree dispersion, 6 channels of application in DSP, as I mentioned, all inside the box. It's all self-powered. And of course, we have an IP rating of 25. So this is usable outdoors in the sun or the rain or the sun. When the C-form connection is terminated on the back, so when you plug your C-form, your 16 amp C-form into the back, then this is a very watertight enclosure and it's completely suitable for any kind of outdoor touring. We have an AES or XLR input and a link out. And of course, we use our ODU. Well, we use ODU, they are not ours. We use ODU connectors for our UNET control network. And UNET is a little bit different to Ethernet. We're going to have a brief look at that in a bit. We also have a, sorry, I'm getting a bit ahead of myself there. Just a few more bits of specification. So it goes down to 52 Hertz. We have obviously variable SPL depending on what the display file, how it has been designed, how you've expressed your SPL profile to behave. But a maximum SPL there of 145 dB in the HF. Of course, as you move down the array, it's probably not going to, the parameter set is not going to use all of that headroom because you're going to be closer to the audience. And this box weighs just a little under 90 kilos. We also have an MLD. This is very similar in format. It has the same complement of loudspeakers, three-way or horn loaded. It's a little bit wider in horizontal as it is a downfill, a little bit wider in the vertical, again, because it's a downfill. And this can be used in exactly the same way. The same parameters in DSP set that we can export from D2 can be used to optimize these cabinets, and they just sit underneath the array which we fly above them. Pretty similar in weight. It's just a little over the 90 degrees. And we have a slightly reduced SPL. As being a downfill, we don't quite require the sensitivity and the high SPL that you do in a standard box, and being that it is a 20-degree dispersion, obviously that energy is spread over a slightly wider space. So let's have a look at the individual components. So 3 HF units there. So we have 3 1-inch neopolyamide compression drivers. There's a little bit more to it than simply just having a horn in front of a compression driver there. There's also a wedge that is placed inside the horn throat. This effectively allows us to flatten the wavefront exiting the horn throat, so it's much more of a cylindrical pattern as it leaves the throat of the HF unit there, and that gives us a wavefront which is much more in line with what we would want in terms of a less curved array. So if we had, as you can see in the top diagram there, a very curved wavefront, if all of the cabinets were at maximum display, this would be ideal, but of course they are not. So flattening off this curve is definitely advantageous, also considering that we have a DSP filter set for each one of these HS devices. It allows us to sculpt the curve of this exiting sort of HF cylinder from the array with our optimization process. Moving on to the mids, we have 2 6.5 neodymium paper mid-range drivers, and additionally there is of course they are horn loaded. There is also a high blade, as you can see, just in front of the in the horn mouth there. This additionally boosts sensitivity, giving us a higher output, but it also improves the consistency of the HF right up to past 4 kilohertz. So as we can see in this graph here, we use we actually cross over our mids there really high up so that those 1-inch compression drivers can take over. Again, that's beneficial. Having these smaller multiple devices gives us less distortion at higher SPLs, so we have a higher quality of audio. But also having our crossover in our mids that high as well, and you can see the output there with the high blade really even all the way up to past 4K, means that we have a single device passing the whole bandwidth of the of speech, so that we're not getting any comb filtering or any issues right in the middle of the speech band, which obviously would not be beneficial. Moving on to the LF, these are, of course, it's a double 12 hybrid loaded, so again, of course, we're using horns and ports, as is the Martin tradition. Obviously, we're gaining additional sensitivity from these devices, but we're also gaining pattern control. And of course, using ports and horns in this way allows us to achieve a very even output. And as you can see there, the ports are tuned specifically to give us this even output, as we have the 2 LF sections plus the port output there, giving us a total sums in blue, where we have a very even output right from 52 all the way up to 320 hertz. Moving on to the MLX, which is the sub which complements this system. This is a dual 18-inch hybrid. This also has the iPal technology back of the amp unit. This actually allows us to monitor what is going in and what is coming out at the same time, and therefore make electronic adjustments to the parameters to make sure that no matter how much power you're using, so low levels or high levels, you're getting the same musical output that you would expect. So why is this relevant? Well, at lower levels, the actual mechanics of an 18-inch driver might be a little bit more lethargic. Therefore, we need to change our DSP parameter set so that we get the same tonal response at these lower levels that we do with the much higher voltage, much higher power, higher SPL levels. Of course, it's an omnidirectional system as standard, as it is a subwoofer, but we can deploy these in a cardioid stack. They can be flown in this manner at the same in the same configuration. We can fly up to 15 of these cabinets. We can also fly these above the MLA if you ever required, and you can ground stack MLA above directly from the flying frame as well. Of course, they have switch mode power supplies, the same as all our MLA cabinets, so they can be run on 110 volts or 240 volts, depending on where you are in the world. Frequent response all the way down to 27 Hertz minus 10 dB is actually plus minus 3 dB, sorry. We can get down to 35 Hertz. Maximum SPL is 150 dB, so this is really a very, very powerful double 18 with a weight of 160 kilos. So if you want to stack them, you might want to ask a friend. Looking inside the cabinet, you can see the slot loaded hybrid there. So we have the ports on the sides and the horns on the front. Again, it's all about increased sensitivity and control. This also reduces the noise turbulence, so you're not hearing that port chuffing when you get right down into the lower bandwidth. Okay, let's have a look at rigging. So, of course, we have all of the standard hardware that you would associate with a touring system. Ground stack bars. We have a distro hanger which attaches to the back of the array, or the back of the flying frame, sorry, so that you can attach the socket for the power and network and signal. It's important to mention also that in our display optimization software, which I would highly recommend looking into if you haven't already, there is a rigging report which we can export, and this gives us all of the angles that we require to deploy our system in the most useful way possible. So just taking a closer look at the rigging, it is a 4-point rigging system, so 2 at the front, 2 at the back. The front arm is stored in the cabinet and is released from the pin in the handle there. The angles range between 0.5 and 7.5, so even if you have a dead hang of MLA, there is still a slight curve to it. The MLD fixed at 13.75 if you're just using one. If you're using a second MLD, it'll be fixed at 20 degrees. We don't normally recommend using 2 downfills. Of course, it's absolutely up to you and depends on the situation that you are in. But generally with 2 downfills, you end up with quite a straight array and a very strong curve at the bottom, which isn't always conducive of the best results. So flying frame, there's ground stack stabilizers, there's rear links and front point pickups. So you can fly the array at the front of the frame. You can also fly the array just on those rear pickup points. That allows you for quite an extreme positive aim angle if required. So if you're flying your array quite low in a theatre, for example, but your audience coverage goes all the way up to the back, quite high in the top, then this is quite a useful tool to be able to send the audio right up to the top there without having to do any kind of fancy pullbacks. There is also a distro hanger at the back. This is where we would attach our socket packs of power. So we have, obviously we have breakouts and all the cables that you require for this. We have our ODU network cables which would be attached to that, analog or AES signal, and of course an XLR for our inclinometer sensor. MLX is also flown off this, and we can also ground stack MLA above it. So we can't really talk about MLA without talking about UNet. And UNet is a proprietary network protocol used for MLA systems. So MLAs do not work on Ethernet. We use a Merlin or a U-hub as a Ethernet bridge. So we have our system processor, for example, would be a Merlin. We have an IP address for that Merlin. We can obviously connect to that with our computer, and we open up our ViewNet software. And then all of our MLA systems loudspeakers connect to that Merlin via UNet. So we don't need IP addresses for the loudspeakers. We don't need to worry about any of those connective issues. All we need to do is have an Ethernet backbone going to our Merlin or our U-hub, which isn't a processor, but we can use our DX4 with that if required. UNet is a bidirectional data stream, so it actually goes around in a loop, and it goes in either direction. So if we do lose a cable, it's not the end of the world. The data just goes the other way. And it also has intelligent node detection, which it measures latency, or it measures a latency between cabinets, so it knows what order they're in. So it's like having an Ethernet network where all the speakers are automatically in the right order all the time, and you don't have to worry about it, which is lovely. Of course, as I mentioned, we have redundancy, as there is that redundant loop, and we don't need IP addresses for all of our loudspeakers. As well as a Merlin processor, which is, I believe, discontinued now. We've now moved on to a U-Hub, which is effectively an Ethernet to UNet bridge, but we also are speccing these with our DX4 processors, so this is just a more up-to-date version with Dante built in. So if you wanted to use Dante with an MLA, then this is how you would do it. With a U-Hub, you also have the benefit of having 3 channels of AES or analog audio wired into the spare pins of the network cable. So going up to the array, we can just send one ODU cable. At the end of that cable, we can break out, as you can see there, into network and signal, making our lives a lot easier. On the back of each cabinet of the MLA, of course, we have our XLR input and a link out. As we daisy chain down the array, we have our ODU input and a link out. And there are, of course, lights to tell you whether there is a connection or a fault on the back of there, and a 16 amp male C-form connector. And this is very much the same on the MLX. As you can see there, it's a little bit of a kind of a concave back panel. That's why that image looks a little bit distorted, just to stop anything snagging in transit. The systems, as standard, come with a master rack that has all the processing, all of the DHCP support if required, the WAP, all the kind of connectivity that is required for this system, and this very handy patch panel. So we have 4 inputs and parallel outs for the Merlin. We then have 10 freely assignable output patches, as you can see there, that would go up to the array or the subwoofers. We also have a WAP with Pyro over Ethernet, nearly forgot what it was, which goes over to our Ruckus systems. And of course, we have our UNet links there in blue, and Ethernet and a copper link there in red. So the difference with the UNet patch there, you'll see that there is only the first and last ports are the only ones numbered. So we only actually have 2 ports. All of the others are just links, so they're just wired in parallel, effectively daisy chaining those 4 links in the middle there. So if we go out to an array, if we go out of this output 1 up to the top of an array, we must then daisy chain down the array and return to the input 2, not the links. That closes the loop. If we have more than 1 array, as we can see in this example, we go out to an array, all the way down the array, and then back into the link, back out of the link down to our subs, and then from our subs returning to input 2 again. So that then closes the loop. I hope that makes a lot of sense. If it doesn't, please give us a shout at the end. We're happy to go through it in any other detail. So here we have some system examples, and you can see the deliberate mistake where this is actually wired incorrectly, which is ideal. But actually, it's just 2 of these blue cables are the wrong way around. But here you can see we have our C-form breakouts going to power our boxes there. We have a signal that goes into the Merlin, comes out from our assigned channels, which we have done in the processor via units, or from the front panel if you require. And this just goes to the top of the arrays, daisy chains all the way back down, and then returns to the rack. And here we have a slightly more complicated system where we have a master rack on stage left, for example, and a slave rack on stage right. So we've just gone exactly the same as our first example there, up to the array, down to the subs, and then returning. The only difference is that we've actually linked via ODU on the Ethernet section over to our slave rack rather than stage rack, sorry. And we've just linked this system in exactly the same way. We could be a little bit cleverer with our MLX systems if required. So for example, if this is a broadside cardioid array, we've actually linked the rear facing, or in this example, forward facing subwoofers from the top going right across the array, and then we go down to the bottom subwoofer and we link all the way back along the bottom. And this allows us to break the array up into two, so that we have our 4 forward facing or 4 rear facing subwoofers on one sort of main DSP set, and then we have our rear facing on the other. And that allows us to treat them in terms of DSP in 2 different ways, so that it's very quick and easy for us to just dial in some delay parameters and the whole system is set. Of course, we need software to control these systems. So we have ViewNet and Display 2.3. So our current reiteration of ViewNet is 2.2. This is our sort of loudspeaker management systems, which we're using to prep our stuff, update our firmware, and then we have Display, which is what we use to optimize our systems. So Display is a proprietary software for all of our MLA products. We also use this software with our wavefront precision systems and our O-line systems. The main difference is that MLA is full resolution all of the time. So there are always 6 channels of DSP in an MLA. It's always absolutely premium. It is the highest level of control you can achieve. Wavefront precision and O-line have variable levels of resolution, and this allows us to decide a budget, for example, for an event, or if it's not a particularly acoustic challenging space, maybe we don't need all that DSP, and those are decisions that we can make. This software allows us to numerically optimize all of our cabinet angles, and it defines our DSP coefficients to give us a handy little preset file which is specific for every single venue we work in. It's a really straightforward workflow. Once you get used to using this software, it is very quick. You just work from left to right, and it really is just a matter of minutes for you to have a very good result in your system. And the DSP file that we create in this software can be loaded directly into an MLA array. So it is actually, once we've defined our array in our ViewNet software, we literally just drag our preset into it. So as I said, there's a very straightforward workflow. We have our venue entry, where we draw an on-axis slice of the venue, and of course we define where our audience is. We then tell the software what each of these surfaces require. Do they require avoiding, or do we just not really care about them? A non-audience area, for example, is just an area that we're not particularly fussed about what happens, but a blue hard avoid area there, of course, is something that we are actively trying to avoid. We then mechanically optimize our system. So Display runs through an algorithm which gives us the best or the optimal acoustic output, and defines display angles that will achieve this for us. And then, of course, we run our FIR coefficients, and this gives us the most even output that we can. It's important to know that this system almost works backwards, where we have a defined criteria for our audience area, and we would then work backwards to the array to say, what do we need the array to do to achieve this response at the audience area? So we're not really bothered what comes out of the box when we're stood right next to it. We're worried about what happens at the audience, and this software allows us to achieve that. So again, it's very simple steps. Venue entry, you set the coverage goals, calculate display angles, and rig the PA, and then you optimize the output and crack on. So the benefits of optimization, well, this system allows us to reduce the spill on stage, or on any location for that matter that we have defined. We also reduce the reverberation in the room, be that echoes or just generally like the RT in a venue. And we can also reduce the noise pollution off-site. So we have this control where we can avoid an area, or we can actually provide an area with extremely even coverage from front to back. We can also use this system to create an SPL profile. So again, in this display software, we can define where our reference point is and how loud it is at the front versus how much it drops off at the back of the audience. So here you can see the array is going to drop by 5 dB from front to back, and we have a very linear transition where it just slopes off across that area. But we can of course sculpt this to our needs, so we can actually make this reduce further from the reference point to -6 dB. So now we are dropping at the front, so it's going to drop by 2 dB from the front to the reference point, but then continue to drop a little bit more steeply to -6 at the back. Equally, we can move our reference point and change our dB characteristics. So now it's going to drop from 5 dB to a much closer reference point, and then relax a little bit as it drops off a little bit slower all the way to -8 dB at the back. So this is, again, something that this technology allows us to achieve very easily within the software. Additionally, as well as refining our SPL goals and giving us a very even response, we can actually account for atmospheric conditions within the software. So atmospheric pressure, temperature, humidity have a huge effect on the output of a system. So here you can see the effects of 21 degrees centigrade, 35% relative humidity versus a response where we haven't taken these considerations into account. So we've really lost quite a lot of the HF. It's starting to tail off around 3K there. So all of that kind of the sort of positive sibilance that you require to have intelligibility is really starting to wane off in a venue that you haven't taken into account air absorption, humidity, and temperature. Of course, we can continuously re-optimize our systems and keep uploading new parameter sets which allow us to maintain an even response even when weather conditions have changed throughout the day. For example, in a festival at midday, the first band comes on stage. It's quite cool, it's quite dry. We've got the PA sounding good, everything's fantastic. But maybe 8 hours later, when the sun's been out, maybe it's rained, atmospheric conditions have changed, and now our array is behaving quite differently. We need to do something about it, and display allows us to do that. So again, just an overview of the benefits. Every time a system is deployed, we have a set of parameters or DSP sets that are specific to that venue, specific to the audience requirements, and specific to the atmospheric conditions of that venue, be that a theatre or an outdoor festival site. We can calculate the best possible array shape for that venue. So we're not just relying on sight lines or human error. We're using mathematics and algorithms to create a much better system designed for that venue. We can use those tools, of course, to deliver a very even frequency response and an SPL response across that venue. We can also create multiple optimizations for each array to suit the audience layout. So for example, if all of a sudden a lot more people turn up and the audience goes a lot further back than you had previously thought, that's okay. We can just change our DSP file, our display file, sorry, to include these people, create a new optimization and upload it into the array. And there's no need to second guess. So when it sounds good at the front of house, you can walk to the front, it will sound good there. When you walk to the back, it will sound good there. So the whole point of this system is to use software and to use mathematics to create a system that sounds hopefully the same everywhere, and therefore when you are mixing, you can be confident that your system sounds the same everywhere. So very briefly, just going to literally just touch one slide on ViewNet there. So ViewNet is our control software for all of our networked products. So whether that's our icon amplifiers that we use with our Wavefront Precision, DX4 processors, or our MLA systems, this is the software that we use to control them. The software allows us to obviously upload our DSP sets in our DTP files, which we upload in ViewNet. We can control our system, so whether that's EQ, whether we're doing diagnostics, if we want to mute or unmute a single cell of the array just to check that it's working. We can manage our presets, so as we go throughout the day, we can keep changing them, and this is all done through ViewNet. Store and record PQ curves. and of course monitor system performance, and very importantly, update and manage firmware. So you can download the most up-to-date firmware library and keep all of your systems up to date so that any bugs that have been found have hopefully been worked out.